Hi everyone, let's talk about the second part of chapter 3. This part has to deal with energy. And as a general definition, energy is simply something intrinsic to a system that enables it to do work. And if you're trying to look at an object and trying to detect how much energy it has, well, it's only observable when it's being transferred or transformed. So we can't see energy unless it's being moved from one place to another. For example, the wind energy turning these turbines, that we can see that happen. And that's energy being moved from the motion, the motion of the air into the motion of the blades. If you had a little meter that could show you how much electricity is being generated, you could then observe the mechanical energy, the rotation of these blades, then creating electricity. Over here, you can, again, you use a meter to detect how much electricity the solar cells are producing, but it's not 100% efficient. So you could also detect how much heat these things are starting to give off as they absorb sunlight and only take some of the energy of the sun to make electricity, and the rest goes into heating the solar panels. And then this poor guy over here, he's all tired. As he does work, he transfers energy in his body to energy of motion in this lawnmower. Just not right at the moment. Okay, there's some different forms of energy that we should be aware of. The first one is called potential energy. And potential energy, it's a good name. When you talk about someone having a lot of potential, it means that they have a lot of ability to do something or achieve something, but they just haven't done it yet. Same is true for potential energy. This is the energy of position. And we have to think of position in pretty broad terms. There's the more obvious position, which might refer to vertical height, like the stack of rocks here. You wouldn't like these rocks to topple over and fall on your foot. And you might worry about this rock hurting the most because it has we carry a lot of momentum because it has a lot of mass. But this top rock would hurt pretty well too because it has a lot of height. So if you want a number for the potential energy of position in terms of vertical height, then you take the mass, multiply it times the gravitational acceleration, which remember to be the weight force, and you multiply that times how high it is. Okay, and you get a number for the potential energy of an object as it moves away from the surface of the Earth. But there's other energy of positions, other potential energy. Like right now, this board right here, you would say has no potential energy in terms of the ability to cast something off of the diving board. It's not compressed. This guy is starting to bend the board a little bit, so it might, if he jumps off of it and there was an object at the end, it would flip over and fall into the water. But you can see here that this board is greatly stretched, greatly bent. And so when he flings himself off, he's going to go up pretty high and fall into the water. So there's more potential energy the way this springboard has been compressed. And then there's also chemical energy. Now these firecrackers are made of materials where the atoms that make up the material are not very stable. And they want to rearrange into more stable positions. So there's a lot of potential energy there. So why don't we see a quick little video in slow motion about firecrackers.
And today we got these earheads to protect our ears. You know why? Of course, something epic like this. Hey, I have a lot more.
These earphones are really good. I couldn't hear anything.
Exactly. But, firecrackers.
Okay, so the first type of energy is potential energy. The second type is kinetic energy. This is the energy of motion. If you like a number for it, you would take the mass of an object that's in motion and then multiply the velocity of that object by itself, square it, and then take half of it. And that'll give you a number for the kinetic energy of that object. And potential energy and kinetic energy kind of go hand in hand. They're kind of opposites in a sense. If you look at this cyclist way up at the top of the hill, looks like he's taking a break and kind of resting there, let's say, at 0 miles per hour. He has a lot of potential energy. He's getting ready to ride very quickly down this hill. And to get up there, he had to exert a lot of kinetic energy. He had to do a lot of work to get that bike and himself up the hill. And as he put kinetic energy in, he's moving very quickly, I assume, riding up to that hill. And then as he goes up the hill, he's going to work harder to pedal that bike, and he's going to start slowing down as his kinetic energy is converted into potential energy. And then he can stop for a minute at the top of the hill, catch his breath, and then just kind of start over the edge. And he doesn't even have to pedal, because all this potential energy, the energy of the height of the hill, can carry him down the hill and start speeding him up and give him a great deal of kinetic energy at the other side. Now, potential energy and kinetic energy, they kind of go hand in hand, but it's not just those two forms of energy. It turns out that all forms of energy kind of go hand in hand. It makes up a law called the conservation of energy. This law states that energy is neither created nor destroyed. It really just gets transferred or transformed. Or in other words, the total energy is going to be the same before and after an event. Okay, so we'll see lots of examples of that in the homework and as we look at other chapters. But let's try out the example of conservation energy with a pendulum. So here's a pendulum clock, and here's some pendulums out in the playground, right? There's some swings of kids playing on the playground, and they're rocking back and forth. So it's helpful to kind of imagine or remember times when you're on a swing. And you kind of remember that the funnest part may have been as you just reach the bottom, you go way up high, and it pauses for a second, but as you slide back through, this is the point at which you're going the fastest, and then it'll slow down again as you come back up. Okay, here's some kids swinging on swings. There we go. Caught this guy way at the top of his arc. That's when his potential energy is the greatest. But as he was going up to this point, now his direction changes, so he has to start coming back down. And there's an instant where he's neither going up or down. He's momentarily at 0 velocity. So he has no kinetic energy, and he has a maximum amount of potential energy. He's at the highest point above the ground. The other boy on the right here, looks like to me he's pretty close to the bottom of the arc. That's when he's moving the fastest. He's at the lowest point, so his height off the ground is not very high. That's his lowest amount of potential energy, but he's moving the fastest, so he has the greatest amount of kinetic energy. So here we got a little diagram of a pendulum sliding back and forth, and on the left side here we got the kinetic energy equal to 0 as it reaches its highest point, and the highest point has the greatest amount of kinetic energy. There's a height here, so PE equals the weight of the pendulum times 9.8 meters per second squared, that's gravitational constant, times whatever that height might be. And the kinetic energy is 0. And when it reaches the bottom here, this is at its lowest point, a little h. And then for simplicity, we just said that this pendulum just kind of barely touches the ground. Not enough to create some friction, but just let the height equal 0. That's the lowest point. So that's where you can begin to measure how high the pendulum goes. Just arbitrarily decide to start measuring from the bottom of where the pendulum rests at its lowest point. Okay, and if you let the height equal 0, then the potential energy is equal to mgh, and h is equal to 0. Anything times 0 is 0. However, all the energy here that you started with, so calculate the mass times the gravitational constant times the height, get a number, that'll be the same number for kinetic energy. It'll equal that number. And if you don't have that number, well, what you can do is measure how fast it's going and how heavy it is, put in the mass, and square the velocity and multiply by 1/2, and you can calculate the kinetic energy that way too. All right. Thanks for watching.